Hello, Dr. Teh. Today, our group is presenting an AI-powered patient health deterioration prediction, a shift in how we understand human health by leveraging generative AI, large language model, small language model, transformers, agentic AI for early clinical warning system. This project addresses one of the most important challenges in healthcare. Every year, hundreds of thousands of preventable deaths occur because of warning signs are missed or identified too late. In many hospitals, patient data is often scattered across vital signs, clinic notes, and in electronic health records, making it difficult for healthcare professionals to gain a complete picture of a patient condition in real time. To tackle this problem, we developed an AI-powered patient deterioration prediction system. We started by using generative AI to create 1,000 realistic synthetic patient records, including both vital signs and clinic notes. We then applied large language model to extract meaningful information from the unstructured clinic text and combine this insight with structured patient data. Using enriched dataset, we train and compare four machine learning models, random forest, XGBoost, neural network, and transformer-based models to identify patients at risk of deterioration. Beyond prediction, we also designed a three-agent agentic AI framework consisting of a data agent, risk agent, and report agent. Together, these agents automate patient data validation, risk assessment, and clinician report generation, creating an end-to-end decision support workflow for patient deterioration monitoring. Ultimately, the goal of this project is to enable earlier detection for a patient deterioration, support clinical decision-making, and improve patient outcomes through the effective use of AI. But four of us from Group 2, Guo Chu Wei, Tan Rui Han, Loo Yung Yi, and Lim Chin Pei, decided to solve it for the data mining project. We didn't just build a model, we built an entirely new early clinical warning system. Over the next slide, we will show how we did it.
Good morning, Doctor. My name is Tan Rehan, and now I'll be presenting dataset simulation and feature engineering. To train an AI model, we first needed a suitable data. Since access to real medical data is often limited due to privacy and regulatory constraints, we generated a synthetic dataset using generative AI. A total of 1,000 synthetic patients were created and stratified into 30% high risk, 35% medium risk, and 35% low risk groups. Each patient record included vital signs such as heart rate, blood pressure, oxygen saturation, temperature, respiratory rate, and Glasgow Coma Scale score. Laboratory measurements including white blood cell count, creatinine, lactate, and glucose were also generated. In addition, a new 2S early warning score, which determined the degree of illness of a patient, was computed for each of them. Beyond numerical data, we also generated clinical text fields such as case complaints, pain descriptions, and patient history. These text records were then processed using Gemini 1.5 Flash API, which extracted several clinically relevant features including severity scores, urgency classification, clinical sentiment, key symptoms, and acuity-related keywords. Next, we applied TF-IDF to convert the clinical text into numerical representations. The most informative unigram and diagram features were selected, and PCA was used to visualize the text embedding in 2 dimensions. Finally, all structures and textual features were combined into a single feature matrix containing 39 features per patient, which was later used as the input for model training and evaluation. And that's it for my part. Thank you.
Okay, good day, Dr. Teh. My name is Loo Yung Yi. I'll be talking about the predicted model development. So now we have the data. Next, we need the engine. We didn't just build one model, we built 4. So There is the traditional workhorse, a random forest tuned with the grid search CV using 100 to 200 estimators. Then we also have the optimizer using an XGBoost model with 300 trees and L1, L2 regularization. Then we also have the deep learner, a multi-layer perceptron neural network, stepping down from 256 to 128 in 64 knots, to 64 knots, optimized with ADAM-W. So then we have also the transformer, which is the semantic brain distributed. We focus on the clinical text. Any one of these models is actually smart, but when they are together, they are better. So our team took 4 models and fused them into a single blended assemble. 25% random forest, 35% XGBoost, 25% neural net, and then 15% transformer. Next, I talk about the model evaluation and results. So look at the results. The sample model hit an ROC AAC at 0.948 and the F1 score at 0.875. What does this actually mean? We fed the results into Gemini 1.5 Flash and our Google Colab notebook, and the LLM summarized it very well. It says an AUC is roughly, the sample model achieved best discrimination 0.94, and an AUC of 0.95 means 95% correct ranking of deterioration versus stable version. This enables corrective intervention and reduces misdeterioration. So we are talking about 91.2% sensitivity and 9.7% specificity. So by integrating those LLM and text feature, we actually boosted the AOC by about 3% over the standard models. We are catching the crash before it happens. Thank you.
Good morning, Dr. Teh. My name is Chin Pei. I will present the following 3 sections, which are the Agentic AI, conclusion, and recommendation for future work. Our Agentic AI system consists of 3 autonomous AI agents working together. First, the data agent validates patient vital sign against predefined clinical threshold. It detects threshold breach and generates alert message, compute the news to score, extract information from text data, and prepare a standardized feature vector for analysis. Next, risk agent performs assemble inference using the trained model. It outputs a calibrated deterioration probability, assign a risk tier from low to high for each patient, and generate recommendation action for each tier. Finally, report agent use the Gemini API to generate a structured clinician report, including patient summaries, key concern, recommendation action, and escalation pathway. All output are recorded in an audit trail and to ensure traceability and regulatory compliance. The Agentic AI pipeline was tested on a batch of 20 patients. The data agent successfully validated all 20 patient records and detect 7 critical breach, while risk agent managed to classify patients into different risk category, and report agent managed to generate clinical report via the Gemini LLM. In conclusion, amongst the 4 models, the weighted ensemble model achieved the best result with the highest AUC F1 score, sensitivity, and specificity. In addition, LLM-based feature extraction improved prediction performance by increasing about 3% on AUC, highlighting the value of unstructured clinical text. Moreover, our Agentic AI system successfully demonstrates autonomous patient triage and clinician report generation, completing the full pipeline in approximately 4.2 seconds per patient. Several areas can be explored to further improve the system. First, future research should focus on validating the proposed pipeline using the real electronic health record and intensive care unit dataset. This will provide a more realistic assessment on the model performance. Next, the system could integrate with real-time IoT device to enable continuous data collection, provide real-time risk scoring and alert. Moreover, future studies should also explore temporal modeling technique that capture changes in patient condition over time, using advanced sequence-learning models such as LSTM. This will provide a more comprehensive understanding of a patient progression. Finally, model explainability should be further enhanced through the implementation of sharp analysis in order to improve transparency and regulatory compliance. That's all for our presentation. Thank you.